So another exercise along the same lines, let's say that you have a square. And that square has a side, the side of the square is 7.1 millimeters. And the potential is given on on all of the corners of the square. So 25 volts that, 20, this one's 20 also over here, and this one is 15. And you're looking for the electric field in the middle of the square. So right here, that's the electric field there. So how to approach this problem? You're given information about the electric potential, and you're looking for the electric field. So the equation that has to come to mind immediately is the connection between them, which is, as we said, delta V divided by delta S with a minus sign will give you the component of the electric field along that direction S, right? What direction to choose? That will be the important question to start with. Right? You can choose the X direction and the Y direction, as we did at the beginning. You know, that would involve actually having information about the potential. If you chose the X direction, right, that would involve you knowing the potential here and the potential here, but you don't know that. You do know the potential at this point. You could extrapolate and say that right in between them, between 15 and 20, the potential should be 17.5, but that's kind of taking the approximation a little too far. You don't really know if that's going to be the case, right? So you don't want to do that. So you want to take directions that are not the X and the Y directions. What would be a good direction to take to look at the difference in potential? Well, you have these two diagonals, right? You could say that this is your point 1 and your point 2, and your delta S is going to be from here all the way to here. Right? That could be a direction. So take your delta S to be that way. And another direction, possible direction, is along the other diagonal. So in one calculation, you will get the component of the electric field along this diagonal, and in the other calculation, you will get the electric field component along this diagonal. Right? And then you will have the both components, which would specify the electric field completely. And before you start doing that, you notice that the second calculation, the one that takes you from this point to that point, will give you a result of 0. Because you're going from 20 volts all the way to 20 volts. So your delta V along that path is 0. Right? So immediately you notice that the electric field is going to have to point, it cannot have a component along this diagonal. It would only have a component along this diagonal. That's going to be your final answer for the electric field, for the direction of the electric field that you're looking for. Right? It cannot have a component along this diagonal. So now you already know in which direction is the electric field pointing. It's along that diagonal. And I drew it pointing towards the 15 volt point because the electric field always goes as a river from high ground to low ground. And the high ground is the 25 volts point. Okay? So I already know the direction. All that remains to be done is to calculate the magnitude of the electric field. Okay? So for the magnitude, I can use that equation. So the magnitude of the electric field will be minus delta V divided by delta S. So this is minus. I'm going from 1 to 2, so I evaluate the potential at the final point, which is 25 volts. I subtract the value at the initial point, which is 25 volts, and I divide by the distance between point 1 and point 2. What's the distance between point 1 and point 2? That distance is the square root of 2 times 7.1 millimeters, right? Square. So the electric field magnitude then will be 15 minus 25, that's minus 10. With this minus, that turns into 10. 10 volts divided by 7.1 times the square root of 2 is conveniently 10 millimeters. So this will give you 10 volts divided by 10 times 10 to the minus 3 meters. So that will be 1,000 volts per meter. That is the magnitude, and the direction we already figured out from the properties of the electric field. Okay? Okay. Any questions about that? So let's work now on going from another possibility, which is given that you might be given the potential in one direction. So let's say that this is the x direction, and you have information about the potential, but not at one point, but continuous. Right? So suppose that you measure the potential along a certain line, and it looks like this. It turns flat between 2 and 4, and it goes down to 0, straight line, at 6 meters. And the height that it reached over here, the maximum potential, is 20, and this is in volts. Let's try to calculate the corresponding plot for the electric field. The electric field in volts per meter. Two, 4, 6. So this is an example of a calculation where you're going from information about the potential to finding the electric field. Okay. So how do we proceed? The connection that we have discussed, there's two equations that we have discussed so far, the connection, to establish the connection. They're related to each other, of course, but let me remind you of them. One is that the difference in potential between 2 points is equal to the negative of the integral of the electric field. And derived from this one, we got this one, the electric field in some direction S is equal to the negative of the derivative of the potential with respect to that direction S. Okay, so which one do we want to use? Well, if we knew the electric field, then we could integrate it, look at the area under the curve, which is what integration means, and that will give us information about the V. That's going to be the next exercise that we do. But right now we do have information about V, and we're looking for the electric field. So this is the equation that we're going to be using. So that equation tells us that the slope of this diagram over here should be equal to the electric field. Okay? Let's start with the easy case, which is the slope of V versus X between 2 and 4. What's the slope of that? The slope is 0. The derivative of a flat line, of a line with zero slope is, of course, 0. So your electric field between 2 and 4 is going to be like that. What about between 4 and 6? Between 4 and 6, the potential is decreasing linearly, right? So the slope, dV dx, is going to be what number? dV dx here, the slope, is equal to what? 20 is the rise, the run is 2, so 20 divided by 2, that's 10. But minus 10, right? Minus 10 volts per meter. So if the slope there is, if the dV dx is minus 10 volts per meter, then the electric field between 4 and 6 is going to be 10, right? So that will be 10 right here. And it is constant because the slope is not changing. Now this figure that you have here, this curve that you have here is a parabola, and it has slope 0 at the beginning. Oh. There. The slope at the beginning is 0, right? So I'm going to start with 0 here. The electric field is going to start to be 0. And the slope seems to be positive everywhere, right? The slope of dv dx is positive. So that means that your electric field is going to be negative everywhere. Now what's happening to that slope? You start with 0 slope, and you're ending with, it looks like 90, but it's not really 90. You end up with some big slope over here. So that slope is going to be going from 0 towards a negative number. How much is that negative number? Say that again. Negative what? 20? The maximum number? That's right. How do you get that? Okay, so you went the other way, right? Yeah, that's good. So minus 20. So he's saying the area under the curve, or under the electric field versus x curve, it's going to have to be 20, right? So how do you get this area to be 20? Well, the base of the triangle is 2. The height, if it's 20, then that will be 2 times 20, that's 40, divided by 2, that will be 20. The area is negative. With the negative of the equation turns into an area that is positive 20. That should be the magnitude of the potential at point 2. Another possibility would be that your potential is a quadratic function. V is equal to a times x squared, starts at 0, right? So when V is 20, and x is 2, your a is going to be 20 divided by 4, it's equal to 5, right? So the derivative of v, dv dx, if v is a x squared, it's 5 times the derivative of 2x, which is 2 times x, that will be 10x. And for x equal 2, that's 20, right? So the electric field is minus dv dx. That will be minus, we said that it was 10x. So at x equal 2 is equal to minus 20, right? Which is the value that we have here. Okay, so two ways to do it, derivative, or as he did it, integrating. Now the other possibility is to have information about the electric field. So let's say that the electric field is a function of x, goes flat between 0 and 2, grows linearly until 4, then it drops to minus 10, flat between 4 and 6, and then it drops to 0. Okay, so what is the plot, corresponding plot for potential as a function of x? And this always, if you're going from electric field to electric potential, there's some additional thing that the problem has to tell you, which is what is the potential at some particular point. So in this problem, I'm going to say that the potential at x equal 4 years, I want that to be equal to 0. Now, why is there that you have to specify the potential? Because when you're going from electric field to potential, you are doing an integral between 2 points. So this equation specifies the difference between the potential at 2 different points. It doesn't tell you what's the potential at 1 point. It doesn't determine that uniquely. It only determines uniquely the difference between 2 points. This delta V is the difference between 2 points. The equation does not say V equals minus E dot ds, right? That's not what the equation says. Careful with that. So because of that, there is an ambiguity there, something that needs to be specified more precisely. So that will be some information like this. I want the potential to be at a certain point, a certain value. Okay? So if that's the case, how would you proceed with this? There's different ways. Everybody has different ways of doing things. What I would do, this is a possibility, depending on the day I might do it in a different way, but let's say that today I want to do it this way. I'm going to ignore this information. I'm going to put that information only at the end. The way I'm going to put that information at the end is to, once I have the plot, I'm going to lift it or lower it to satisfy the condition that the potential at x equals 4 should be 0. Okay? So let me ignore that for a moment, and let's just start by this. The connection between the electric field and the potential is through the area, right? So between 0 and 2, the area of under the curve should be the changing potential, right? So the area is 0, so between 0 and 2, I have 0. Okay? Between 2 and 4, what happens to the electric field is growing linearly. The area, when you are at x equals 4, what is the area under that curve? I see that the curve, the area is going to be a positive number, so my potential at 4 is going to be a negative number. I know that for sure. I know that the shape is going to be a parabola, right? Because the integral of a straight line is a parabola. So it's going to be a parabola that's going to take me from here to some negative number. So it's going to go like this. What negative number is that? The difference in potential between x equals 2 and x equals 4, the integral says that should be the negative of the area of that triangle. The area of that triangle, I didn't give you, sorry, we're missing the value here. So that is 20. Alright, 20 volts per meter. So what's the area of that triangle? So you have the height, which is 20, the rise is 2, so that's 40 divided by 2, that's 20. So I know that this thing is going to have to go down all the way to minus 20 volts. Okay? Now what about between 4 and 6? Between 4 and 6 we have the area under that curve is 10 multiplied by 2, that's 20. The area is minus 20 because it's under the x-axis, minus 20. With the minus in the equation for delta V gives you 20, right? So the potential is going to grow, it's going to increase by 20 between this point, which is x equals 4, and x equals 6. Should increase by 20, and it should be linear because the electric field is constant. Okay? So we're going to go from minus 20 all the way to 0, right? It's going to increase by 20. Okay? And after 6, the electric field is 0, the area there is 0, so the potential becomes constant there. It's not changing anymore. Okay, so I'm done with that. Now I need to, and that will be easy to forget, that I have to satisfy this condition. So how do I satisfy that condition? The condition says that the potential at x equals 4 should be 0. This is x equals 4 over here. This is 2 and this is 6. So how do I do that? Lifting a function by a constant doesn't change the differences, the delta v's between the different points. So just by moving this plot up or down, I'm not changing the physics of it. The connection between the electric field and the V will be unaltered if I do that. So I'm going to have to move this plot. So all I have to do is move it 20 up to satisfy that this point has potential, that the potential at x equals 4 is 0. So the plot is going to end up looking like this. Flat all the way to 2, then is a parabola, touches 0, straight, and then constant. And that's your final answer for the potential as a function of x. Okay?